Hello everyone, I am Mr. Ashish Chaudhary, Assistant Professor of Mechanical Engineering Department from Vidya Prasar Mandal's Muharji Parshuram College of Engineering, Bhubaneswar. Today we are going to see in our fluid mechanics lecture series one of the chapter as the kinematics. In that we are going to study the continuity equation. Before going to study the continuity equation, first we should know about the rate of flow or discharge. So rate of flow or discharge, it is defined as the quantity of the fluid flowing per second through cross section of a pipe or channel. Okay, suppose we consider any fluid will be flowing through the pipe, then at a particular section how much quantity of that fluid is passing per second, it is called as the discharge. So gases are generally compressible fluids, and we can measure the discharge in terms of mass flow rate. It has unit is kg per second. Then liquids, these are generally considered as incompressible fluids, and we will measure the discharge in terms of volume flow rate. It has unit is meter cube per second. And to find out the discharge, first we should know about the cross sectional area of a pipe. So we will consider cross sectional area is A in meter square. Average velocity of liquid which is passing through that pipe, it is V in terms of meter per second. Then discharge is calculated as Q is equal to area into velocity. So area into velocity we will consider, we will get it is meter cube per second is the volume flow rate or the discharge for the liquids. Now after that, now the continuity equation. So continuity equation, this equation is based on the conservation principle of the mass. That means my mass neither be created nor destroyed. It is only transfer from one place to other place. By using same principle, we will find out the continuity equation. Okay. So to find out the continuity equation, we have considered here is the pipe section, one of the pipe section. At inlet we have considered section cross section as 1 and outlet we have considered the section as 2. At inlet we have the area of pipe is A1, velocity of fluid V1, and density of that fluid is ρ1. At outlet we have the cross sectional area is A2, velocity of fluid is V2, and density is ρ2. Okay. Now at cross section 1, mass flow in the section 1 is calculated by density multiplied with volume, density multiplied with velocity multiplied with area. So by using this one we can directly calculate the mass flow rate. Okay. Velocity multiplied with area is the discharge or volume flow rate. If you multiply that with the density, we will find out the mass flow rate. Okay. So this is about that cross section 1. Similarly, at mass flow out to the section 2, it is equal to density ρ2 multiplied with velocity V2 multiplied with area A2. And by using conservation principle, we know that mass is only in transfer condition, so we have mass flow in is equal to mass flow out. So based on that, so we'll equate these two. We have ρ1 V1 A1 is equal to ρ2 V2 A2. Okay, but for incompressible fluid flow we have density is always constant. So density as ρ1 is equal to ρ2. So if we substitute this one, we have the continuity equation is simple form is we have the product of area with velocity at one section is equal to product of area into velocity at other section. So this is called as the continuity equation. Okay, so this is very simple form of continuity equation. Okay, now we will see the continuity equation in the Cartesian coordinate system. So for Cartesian coordinate system, here the Cartesian coordinate system is the system we will consider here the coordinates in terms of x, y, and z. Okay, so and these coordinates are perpendicular to each other. So for that we have the coordinates are x, y, and z. These three directions are perpendicular to each other. To find out the continuity equation in this coordinate system, we have considered here the parallel pipe element which has dimensions dx in x direction, dy in y direction, and dz in z direction. Okay, so to find out the continuity equation, we have just named here this parallel pipe element as the face as A, B, C, D, and E, F, G, H. Okay, so we have pointed out here the corners of this parallel pipe element. Now if you see here in the X direction, we have mass flow rate in is available in X direction. Similarly, mass flow rate out is available in X direction in opposite phase. Now here mass flow rate in Y direction is available in this phase, just like A, B, F, E. Okay. Similarly, the mass flow rate out in Y direction is available through the cross section as C, G, H, D. Now in Z direction, mass flow rate in is available through the cross section as B, C, G, F, and it is outlet of the mass flow rate in Z direction as M dot Z out is A, D, H, E. So this is about the element. Now through that element, the mass flow rate will be taken in and taken out in all three directions. Okay. So for that, we know that mass flow we have already seen in previous simple form of continuity equation as mass flow is calculated by using density multiplied with velocity multiplied area of cross section through which the mass is moving. Okay. Now here to find out the continuity equation, we have considered here velocities available or the velocity in the three directions. So there are the components of velocity. So here the u, small u, we have considered here the velocity component in X direction. Small velocity, small v, is velocity component in Y direction, and small w is equal to velocity component in Z direction. Here we have considered the fluid having the density constant. So rho is equal to constant. So now we will see mass flow is available in X direction. To find out the mass flow in X direction, so first we will find out the mass flow in X direction here. M dot X in, this is will be passed through the cross section A, B, C, D. So A, B, C, D have area is dy multiply with dz. Okay, so here M dot X in is equal to density multiply with velocity. Velocity in X direction we already find out, it is u, multiply with area. Area is dy multiply dz. Now this is about the inlet of mass in X direction. Similarly, mass outlet in X direction as M dot X out, and this is through the cross section E, F, G, H. This area, if you calculate it, it is again dy multiply with dz. Dy multiply with dz. Okay, but if you see, to find out this mass flow rate out, first we will calculate it by using Taylor series of expansion. Okay, that means this mass flow will in X direction, and there is a change in this mass flow according to the dx distance. So for that we have the initial mass flow plus change in the mass flow, which is extra, is available in this dx distance. So we have rho u dy dz plus daba by daba x in bracket rho u in dy dz, that is change in this mass with respect to distance dx. Okay, if you solve this one, we have rho u dy dz plus daba rho u by daba x in bracket dx dy dz. So we will multiply this dx into this bracket, so dx dy dz, because this dy and dz distance are not changing according to the distance x. So that's why this is a constant one. So we can multiply this dx with this area, so we will get here the volume dx dy dz. Now net flow in X direction. So net flow in X direction we can calculate as mass flow rate in minus mass flow rate out. So similarly m dot x in minus m dot x out is equal to here, by using this one equation same as it is rho u dy dz minus this mass flow rate out in bracket rho u dy dz plus daba rho u by daba x multiply dx dy dz. If you simplify this one, we will get here m dot x in minus m dot x out is equal to minus daba by daba x rho u dx dy dz. This is our equation number 1. Now mass flow in y direction. To find out the mass flow rate in y direction, again we will consider the diagram. So mass flow rate in y direction, if you see here m dot y in, so this is inlet mass. So this is will be through the cross section area as ABFE, and this is equal to dx multiply with dz, dx multiply with dz. So based on that, here we have density, velocity in y direction multiply with area, dx dy. So in previous one we have calculated the mass flowed out in x direction by using Taylor series of expansion. So similarly we can calculate here mass flowed out in y direction. So if you see here we have the mass flowed out in y direction. So if you see m dot y out, okay, this m dot in y, m dot y in will be changes with the distance dy. This is already one, and there is extra added due to the change in the distance dy. So for that we have m dot y out is equal to this one as it is, rho u dx dy plus change in this mass in the distance dy. So da bar rho v by da bar y multiply with dx dz multiply with the distance dy. Okay. If you simplify this one, we have is equal to rho v dx dz plus da bar rho v by da bar y multiply with, so just we calculate the multiply this dy into the bracket, because these dx dz are not changing according to the y direction, so that's why this is constant. So dx dy dz. Okay, so this is our equation number as 2. Now to find out here net mass flow in y direction. So already in x direction we have calculated. Similarly m dot y in minus m dot y out is equal to rho v dx dz minus in bracket rho v dx dz plus da bar by da bar y multiply with rho v dx dy dz. If we simplify this one, this term gets cancelled. We have the remaining term is this one, but in minus sign. So m dot y in minus m dot y out is equal to minus da bar by da bar y rho v dx dy dz. This is our equation number 2. Okay. Now similarly we can calculate the mass flow rate in z direction. So we have m dot z in is equal to rho w, rho is the density, w is the velocity in z direction multiply with the area. So if you consider calculate the area in z direction, we have area is, so this is inlet direction of the z, so dx multiply with area dy, dx multiply with dy. So by using this one we can calculate the area. So here, so rho w dx dy. By using Taylor series of expansion, m dot z out is equal to initial mass plus change in mass with respect to distance dx. So da bar by da bar z rho w dx dy multiply with dz. After simplification we have m dot z out is equal to rho w dx dy plus da bar rho w by da bar z multiply with dx dy dz, because these are the constant one. Now net mass flow, net flow of mass in z direction. Similarly m dot z in minus m dot z out, after subtracting this value from inlet value we will get minus da bar rho w by da bar z dx dy dz. This is our equation number 3. Now after supplying all this mass flow in and out flow, there will be net rate of change internal mass of this element. To find out this one, we have calculated here the net rate of change of mass flow into the element. So this is find out with respect to time, because mass we have calculated by using density multiply with volume. So density, we know that formula of density is equal to mass upon volume. So if you multiply with density with volume, you will get the mass. Okay, similarly, so by using this one we have calculated here. So net rate of change of mass, that means the change in mass with respect to time. So da by m dot by da by t. So this is equal to da by da by t, and this is the mass density multiply with volume. So density of the element at the fluid inside of the element is rho multiply with volume as dx multiply with dy multiply with dz. Okay, So net rate of change of mass with respect to time is da by m dot by da by t is equal to da by rho by da by t multiplied with the volume dx dy dz. This is our equation number 4. Now by using a mass conservation principle, we have rate of mass flow into the element minus rate of mass flow out of the element is equal to net rate of change of mass flow into the element. Okay, so we have already calculated this. We have already calculated net rate of mass in x direction. Net rate of mass in x direction, this one, adding with y direction, this one, adding with z direction, this one. That means adding equation number 1, 2 and 3, we will get net rate of mass in and mass out, net rate of mass flow in and out. So this is the addition here, minus da by rho by da by x, rho u by da by x, dx dy dz from equation number 1, minus da by rho v by da by y multiplied with dx dy dz from equation number 2, minus da by rho w by da by z multiplied with dx dy dz from equation number 3. This is equal to net rate of mass flow with respect to time. So this is from equation number 4. We have substituted here da by rho by da by t dx dy dz. After simplification, if you see here in the equation at left hand side and right hand side, we are getting the volume element. So we will divide this equation by volume dx dy dz. We are simplifying equation as minus da by rho u by da by x minus da by rho v by da by y minus da by rho w by da by z is equal to rho u da by rho by da by t. Okay. Now we will simplify this equation as here da by rho by da by t plus da by rho u by da by x plus da by rho v by da by y plus da by rho w by da by is equal to 0. So just we have simplified this equation. Okay, so we are taking this minus sign, minus terms at the right hand side. So we are getting rho u da by rho by da by t plus all these terms. So this is again here, and this is equal to 0, and this is called as a continuity equation, generalized continuity equation, which is applicable for compressible flow, incompressible fluid flow, steady flow, unsteady flow, uniform flow, non-uniform flow. Okay, so now to find out the steady flow, you know that for steady flow, any property, if you consider, this is not changing with respect to time. So for steady flow, if any property we are taking with respect to time, this is always 0. So all the properties are not changing with respect to time. So density is not changing with respect to time. That means this term becomes 0. So da by rho by da by t is equal to 0. So our equation becomes da by rho u by da by x plus da by rho v by da by y plus da by rho w by da by z is equal to 0. Now if you take rho common and multiplying all the at the other side, it is equal to 0. So we have da by u by da by x plus da by v by da by y plus da by w by da by z is equal to 0. This is the continuity equation for steady and incompressible fluid flow. Okay. So if you see here, this equation contains only velocity components available in x, y and z direction. So this is the continuity equation available in Cartesian coordinate system with steady and incompressible fluid flow. If you consider compressible fluid flow, we have to multiply here the density. Okay. Thank you.